worked as associate professor in Department of Information Technology at MIT School of Engineering under MIT Art, Design and Technology University, Pune for 2 years. Currently, he is working as an assistant professor in the Department of Computer Science and Engineering at IIIT Nagpur. He has supervised more than 14 PG projects. He has also supervised more than 24 plus UG projects. He has 4 research publications in Yale and Scopus Index International Journals. He has research publication in international conferences and 10 research publications in national conferences. He is also serving the technical for different reputed journals, delivered many talks in FDP and workshops, also handled many administrative responsibility at the institutions. His area of interest includes delay tolerant vehicular delay tolerant networks, mobile social networks, Internet of Things, and machine learning. So now I request Dr. Milind Penurkar sir to start his session on decision tree.
Yeah. Good morning, all.
Yeah, sir, you can start.
I'm audible. Yeah. Thank you, sir. Thank you, Jitan
Yes,
sir, for inviting me. Thanks a lot for giving me an opportunity.
Yes.
Good morning, all.
Yes, sir, you are audible.
Okay. Yeah. So let me share my screen. Yeah. So is the screen visible as well?
Yes, sir, screen is visible.
Yeah. Okay. Fine. Fine. So good morning, all. Although Jitendra sir has introduced me as an expert in so many areas, but well, as far as this area is concerned, it's again a new area for me individually, and in this area, recently started working in the area. And as Jitendra has given me an opportunity, I will try to give my best for this particular session. Okay, so today we will be starting with machine learning, supervised machine learning kind of technique or algorithm, which is used for the purpose of doing supervised learning. And there are so many other algorithms in supervised learnings. Well, we have multi-layer perceptron, single layer perceptron, we have logical regression, logistic regression, and so on. But then this is one of those which is used for the purpose of finding out a model, but using a tree kind of structure, right? So that the agenda would be to go ahead with understanding of what the supervised and unsupervised learning would be, just introduction, and then we would move to the decision learning or decision tree learning, where we would be learning the stuff using decision tree. So that's the reason it is called as decision tree learning. So we'll try to use learning as a mechanism under machine learning, which would be used for the purpose of generating a model. And we will see as to how this model could be the best one which fits the training data or training instance as such. So that is one thing. And then we will see one of the algorithms called as ID. This algorithm is, there are many algorithms like chest or we have C4.5 and then ID3. Multiple algorithms are there, but then we will try to take one algorithm called as ID3 algorithm and try to see how this algorithm is used to construct a decision tree with whatever attributes that are given and the training instance that is given. And then we'll take one example on this decision tree learning. Fine, so that would be an agenda. Just to start, we have machine learning. You already know so many lectures would have gone through of this particular workshop in ATL, or you would have also, all these participants would have already known about what a machine learning is. Introduce an ability to automatically learn and improve from an experience without being explicitly programmed, right? So given some input at a training instance, we would require some algorithm which will every time improve, or we will make sure this algorithm give you a model that will fit the data. So we would like to have an accuracy, as an more accuracy as far as the model is concerned, right? So two fundamental or broad categories that we have. One is supervised learning. So in supervised learning, we have given a data input X and output Y. The learning algorithm will generate a model, right? And for new input X, using this above model that we have generated, we can output Y. So we can classify or predict. So given this data instance, already the learning algorithm will generate a model. And so later on thereafter or henceforth, whatever new input X comes around, using the above model, we can output Y or classify or predict. So the algorithms under these categories in general, the broad stuff that I have listed out here is one is classification, a classification problem wherein output variable is basically a category. So it could be a disease or no disease. Given the training data instance, we say that a particular person would result into a disease. We would predict that a particular disease would happen or this disease would not happen. Right, and then second is regression problem. So generally for continuous variables or real valued variables, wherein we see that a output value is basically a real value, e.g. weight. So you cannot have weight as use of the weights. So those are continuous values. We never know what are those values. I mean, we know those values as continuous input, or even the age. It cannot be yes or no. It can be a continuous age. You can, of course, divide between 0 to 10, 10 to 20, and so on. But well, that is another example, and height could be another example in those. Okay, so and in under unsupervised learning, we have given a data input x1, x2, x3, and so on. Let's say xn. The learning algorithm will generate to check if certain data is based on the similarities. We do not have y or output out here as an instance. So given an input data that is available, our learning algorithm will generate a cluster to check certain data items classified based on the similarities. So everything has to be done based on the input. So that's the reason it is called as unsupervised learning, right? So based on the similarities, we could check what is going to happen with the output. So here we, instead of classifying, we would be clustering, right? So the general algorithms which would present in this case are again listed in a broad categories. We have a clustering problem where we would like to find the inherent groupings in the data, whatever data available. So, for example, you could group the customers by their purchasing behavior, what kind of it could be the medium level and could be high reach and so on. So based on that purchasing behavior. And I could have an association problem wherein an association rule learning problem, we could say, to find out the rules that describe you have a large portion of data such as people that buy X also tend to buy Y. So you have this data that is available with you where you have we would like to give something related to an association where if some of the customers they buy milk, they would be or they would try to buy butter and so on. So that's the kind of association that we are talking about here as far as association problem is concerned. But that comes again under, as I said, the unsupervised learning. Right. So in unsupervised learning, we only have an input, but we'll be trying to find out or clustering or doing the association. Okay, so just to continue the discussion on supervised learning, because our topic today is on decision learning, which is a kind of supervised learning algorithm. Here it is what we would like to do. We have an X and Y as input instance, the data training instance given to us. We input 1, output 1, or input 2, output up to N. And we have a learning algorithm which says that this learning algorithm will give you a model. Right. So based on whatever learning algorithm we have, we will be getting a model. Now, the question is how many models we could have. So depending on tuning the learning algorithm, we'll tune it. The training instance available. Every time we'll have more learning that is available because the training data would also increase and it would be over the time becomes accurate. Then we will be giving the model, and then having this model around, given a new input X, using this model, I can output Y well, that output y could be a classifier or it could be a predictor, right? So we can predict the value of that particular instance. So as I said, based on the data, you could predict whether a person would have a disease or she or he would not have a disease. Or you may have a specific type of disease that that particular person would have or would not have based on the training instance that is available with me, right? So that's the kind of stuff that we are talking about as far as learning is concerned, right? So before we move to the decision learning mechanism, I would like to have some terminology that we would be using, and that terminology would be used, or it would help us to go ahead with the in a clear way. Training examples or training set or data instance is also called as, or it's called as an example set that is given to us. So for example, we have a for playing tennis and we would like to know whether a particular player on a particular day, let's say on Saturday or Sunday, we would be able to play the tennis or not, depending on the different conditions that are offered. So for example, conditions means I'm talking about those features or attributes or different variables. So I'm like, we have a temperature. What is the temperature of today? This data is available with me. What is the humidity? What is the outlook, whether it is rainy, whether it is humid, and whether it is sunny, and so on. So all this is available with me as an instance. So these features or attributes are these attributes that I'm talking about. And play tennis would be an output. We say the output kind of attribute which we would like to predict based on the values of the features or attributes. So I have training examples available. I have features available of the training example, and I have a feature set. So what I mean by feature set, a set of attributes that we are interested in. So for example, I have I'm interested out of let's say 1,000 such examples in the training data set that have been given. Am I interested in only few features or attributes based on which I would like to predict the value of a particular attribute? So that's what I would like to do. So training example, clearly the entire instance available with me, the features, the individual measurable property, which is probably any, and out of the given set, how many attributes that we would be interested in. So that's the terminology that we have. All right, so here we go. Then we have an introduction on decision tree. It's basically a supervised learning mechanism. As I spoke about, the supervised learning can be done or represented in a few ways. We have linear function, of multivariate linear function, about descent, single layer perceptron, multi-layer perceptron, and so on. So there are multiple mechanisms by which supervised learning can be done. So here, descent trees is also one of the supervised learning mechanism where we have training instance of input as well as output that is already available, right? And then the descent tree learning would be a method for approximating discrete value target function. So please note that we are interested morely in discrete valued target function. So I would like to know whether a is going to be there or it is not going to be there, yes or no. Such a kind of target function that we are interested in. Although we also, at the end, I would also show you one continuous or a real valued variable wherein we also could be doing tree learning, but well, decision tree learning is mostly used for the purpose of discrete value target, right? So in this case, the learn function that I would have is represented by a decision tree, right? So we would be interested in the forming a learning as represented by a decision tree. So we can say it is a machine learning classifier in the form of a tree. So it is basically a machine learning classifier in the form of tree structured classifier, we can say. And the instances classified by decision tree. Instances means I'm talking about those training instances based on those attribute values. The instances are classified by decision trees by sorting them down the tree, by sorting them, remember this, from down the tree from the root to some leaf node, right, which provides the classification of the training instance. So that is how so this is just a definition. So let's take an example where we would be seeing what is the descent tree, right? So I was talking about sorting down towards the leaf. We have some example scenario here where I have my training data available. So what is there in the training data? The training data has the information about whether a loan has been approved or loan has not been. I mean, I would like to loan is to be approved or loan is not to be approved for a particular applicant, but then I should have a data that is available. So the data that would be available for you is the person is whether it is employed or he or she is not employed. Then if he's employed, whether there is high credit points or low credit points kind of stuff. And if the person is not employed, then we have income of that particular employee. Let's say this data is or these attributes are available with me. But then that doesn't happen on day one. As you know, data will take some to generate. It gets generated over the period of time. And this, given this particular data that is available over the period of time, what I would like to predict is when a new applicant comes around and this new applicant wants to take a loan, can the bank where this data is available uses the dysentery learning whether a loan can be approved or loan can be rejected. Right? So that's the thing that we'll be talking about. So this dysentery that gives you the clear picture about. So let's say the person is employed or an applicant is employed. If he is employed S, then we see immediately I won't be giving a loan or a put. So we will again another attribute where we would see whether he or she has high credit points or not. So if he has high credit points, yes, all this he has high credit points, then the loan is approved. And if the high credit point is no, then we'll see the instances where the loan can be rejected. On the other side, if the applicant is not employed, then I will have no income. Employee is not employed, then we will go and check out the income. The income is high, then I say loan is approved. And income is low, then I would say loan is rejected. So this is a general example. We will see as to how we would go to test the data. So at every node, right from root node, we have a testing on the attribute and the values of this. So this attribute employed would have values. Now here you could see there are discrete values, and these are again Boolean kind of classification values. They are not continuous or they are not real valued kind of stuff. So here it is discrete, saying employed S or no, high credit point S or no. So at every stage, we would be testing the attribute and the values. Based on the values, we could go on left hand side or on right hand side of the tree, and then we actually could go again to check the next attribute, right? But then on what basis I should choose which attribute to choose first, which one is to be root node, the next attributes that are to be chosen, and on what basis we would be choosing those attributes, and what basis those attributes would go down till to form the tree, how much depth we would have for the tree, how many such a subtrees can be constructed. So all are these issues that are what we are going to handle today in the next part of the presentation, right? So this is one example. Let's say there's another example where I was talking about Saturdays where a player play tennis. So given a training data instance, I would like to know whether on a particular Saturday or let's say particular Sunday, a player or let's say someone like me would like to play tennis or not. So given play tennis training instance, let's say Outlook is what I have chosen as a root. Now again, the question is why Outlook? So we will come to that shortly. But then whether my Outlook is sunny, whether the current Outlook is overcast or it is rainy, then if it is sunny, then I'll go for a humidity, and whether my humidity today is, let's say today humidity is normal, then yes, there is a chance for playing. And if humidity is high, then there's no chance. So no, you probably won't be recommending or predicting that tennis. But if Outlook is overcast, then we simply say that yes, all the training instances are positive. I'll come to that, what I mean by positive and negative. But in that case, it will be an yes. And if my Outlook is rainy, then I would check out whether the condition are. So if it is strong, then I recommend or predict that no, on particular Saturday we should not be playing. But if the wind is weak, then we would say yes, we would be able to play it. Right. So that's the example of a descent tree where we would like to construct the tree. We would like to learn. The learning is going to happen with the descent tree, and based on this, we would predict the output of it. So if you see from outlook, sunny, humidity, normal, you come to yes. From outlook, overcast, you come to yes. And again, coming from outlook, rainy, wind, and then weak, you come to yes. So if you see, some of them are giving this as yes, and of course, some of them are giving no. So on what basis we should be choosing the attributes? On what basis the tree could be constructed? How much should be the depth of the tree? So all those things would come in. So is this introduction clear? I mean, is this clear so far? Is the speed is also clear? Kindly let me know. Okay. But yeah, we in this case we have not considered. Yeah, in this case we have not considered. If you would have a sunny day, then probably I'll come to the training instance, and there we will see how that would look like. Fine. Yeah. Okay then. Right. So given the training example or data instance, using the past applicants who had applied for a loan and the data is available, the training is with me. And as I said, there are various attributes like employee, income, the high credit points, and so on. What we really would like to do is from given training day, from a given training set, a dysentery can. And for a new applicant that comes around, one can predict its value. I mean, what is the value based on a dysentery, the prediction, so that a applicant can go for that particular loan accepted or loan rejected, right? Okay, so the nodes that I was talking about, there are a couple of nodes. One is called as descent node and other is called as leaf node. So first is the descent node. So in node, it provides a test and through which one can decide in which direction to go, whether we would like to go on left branch or we would like to go on a right branch, as we have seen. So test on feature at every attribute or at every node, we would be testing the and its value. Based on its value, we will be going on the left hand direction or right hand direction. So test on feature, if it say yes, then I would have this. So again, this could be the multiple descent nodes. Here, if you see descent node on left hand side as well as descent node on right hand side, the meaning of this is we have not yet predicted the value. So we need to again, construct a tree or expand the tree further. So test to be done is on attribute or feature in the example training set. And as I said, in general, we only consider two outcomes. So in most of the presentation, I would be talking about only two outcomes, but where at the end, I would also be talking about continuous attribute. So mostly discrete attributes, play tennis, yes or no. And as I said, you may have continuous attributes as well. But in general, mostly the descent trees are used for the purpose of this discrete. They suit for discrete valued kind of attributes. This is one. The second one is the type of nodes called as leaf nodes. So here in the leaf nodes, we indicate the classification of an example or a value of an example. Value of an example means this the prediction or classification value. So indicate the classification of an example or value. So you start at the root node, descent node, and reach the leaf node through testing multiple such attributes so as to go to the end. And at a leaf node, we would have a of whether you say, let's say, an example, play tennis, whether you would be able to play tennis or not. Right. So that's the leaf node. So generally, if you see, the leaf node is represented as a complete rectangle. No. Leaf node, right? So how could there will not be any expansion further. The moment you reach to leaf node, we will be stopping, right? So no further expansion after leaf node. Okay, so start at the root node. So the value could be of an example for the classification or even a probability. So why I'm saying a probability? So given a training instance and I have, let's say, a huge number of records there in the training instance, how much tree construction of the tree would be? It could go and go on, go on, and then we would not be able to get the leaf node at all, because there are so many examples and every example will not have all positive or all negative. Positive means all play tennis yes, negative means no. So there are some of the attribute might result into, let's say, 60 of yes and 30% of no. Again, on some another attribute, you try to expand the tree, it would be 80%, 20%, and so on. So I do not find like 100% and zero. So in such a case, I say that, okay, let me stop constructing a tree and declare that 80% of the time I'm going to get play tennis yes with a probability of 80%. And 20% I will leave. I say I cannot do this as 100% because there are some errors in my attribute themselves. There are some errors in my training data itself. Therefore, I won't be able to go with an exact yes or no. Therefore, that time you can give a probability, right? So that's what I mean by value would be a probability. It may not be classification directly in such a case, right? So this could happen in any of the records, any of the training data instance. Okay, so that's the reason I was talking about the target problems for dysentery learning in that sense in general will be, we would apply in the real world only to those problems where my instance a fixed set of attributes. The first is instances are represented by attribute value pairs. Every attribute would have certain fixed set of attributes. I will not have, much more attributes than this. So, for example, temperature, its values are hot, mild, cold. So we have limited stuff. And the target second one is the target function has discrete output values. So that's what I was talking about. We would have a Boolean classification, e.g. yes or no. And then there's a problem. Okay. So is it the case with all? Okay, so I think probably there is a problem with one who is having there. Most others have been able to hear it. Is it the case? Okay, let me continue, and then if again something comes up, kindly let me know. Okay, fine. Okay, so another problem is the problem that I can target training data may contain missing attribute values. So what I mean by that is some of these attributes, they may not have a value. For example, dysentery methods you can use even when some training examples have unknown values. So I do not have any value. The humidity of the day is known for only some of the training examples, and for some of the training examples it is not known. It is still absolutely fine, although we say that's going to be because based on some other attributes or the strength of the other attributes, the model would be generated. So that's the problem. But then yes, we can use such a for such a problems this dysentery. Okay, so this dysentery learning in general is applied to problems such as learning to classify, right? So diagnosis of medical condition. They will, see, those values will not be taken into consideration. Only those values. For example, as I said, uh, if there are, let's say, 100 values, of which only two values are, so only those two values will be taken, and on the rest of the attributes, then the dysentery would be found. So that's what I mean by the missing values would be treated. And if nothing comes up on that attribute, in general, we would not expand the tree. That is how it is going to be. Fine. So dysentery learning in general is applied to learning to classify, for example, diagnosis of medical condition from the pattern of whether a particular disease could be yes or no. So in medical field, this is used as an application. And even in for loan applications, for loan applicants, we have a likelihood of defaulting on payments of their EMIs or something. So we would have a data available, and then based on that data, we would see some of them are defaulting on payments based on the history or based on the training instance that is. So in such a case, we could use it because there some of the data might not be available because some of the payments are not been done for some of the customers, right? So that. Okay, so let me continue and then we will go in little more depth now. Now let X be the set of training examples. Let's choose a test on attribute. Let's right now choose some random attribute among this set of the training instance, which attribute or features test. So let's take one, A1. Let's assume that A1 equal to S. It means, let's say A1 is the example here that we have taken with humidity as, let's say, high or humidity as a normal. So in such a case, if let's say A1 is S, then I get X1 as a training instance where I, with A1 equal to S, the values for, let's say, play tennis. Some of them are saying play tennis yes on humidity with value, and some of them are saying with humidity no, no, with A1 equal to no. So in this case, I would say humidity. So no, I would not like to play tennis. But then based on these two attributes with values A1 equal to S and A1 equal to no, X1 is a training instance that I get with A1 equal to S. And I get X2 as subset because X2 now contains only those examples where A1 equal to no. Understand this. A1 equal to S, I would have X1. So of course I reduced my training instance from A1 and then not A1, I'm sorry, this should have been X. Please understand that when I started with A1, the training instance was X. I got X1. A1 equal to no, I have got X2. Right. So here, when I say stop, it means there's a leaf node. All the examples here are positive. All of them based on A1 equal to S are saying play tennis. And if A1 equal to no, some of them are saying S and some of them are saying no. So examples in X2 contain different outputs. So in that case, I need to expand X2 further. So that is the case. So all examples output, then X1 need not to be expanded further. And examples in X2 says contain different outputs. So you need to expand X2 further. So as I said, X1 and X2 are the subset with example that have A1 equal to S and A1 equal to no respectively. So let's take another example. So X is a training instance with attribute A1. I say yes, I go to A2. A1 equal to no, I go to, let's say, A4. As of now, I have not decided whether X2, where in A1 equal to no, needs to be expanded further or not. But I have expanded X1. Now with A2 has S and no values, X11 and again X12. Would have all, let's say, all positive values in X11, therefore I can stop. And for A3, X12 to be expanded yet. Right. So now whether I should expand X12 first or X2 first. So if you go from, let's expand X12 first and then probably expand X2 and so on. So all outputs in X11 are positive. So therefore we are stopping. At every step we have to take decision whether to stop or grow further. Right. Now, as I said, if it is no, I mean the values in the set that I am going to get, if they are not all positives, some of the positive and some of the negatives, then you probably have to expand. But the question is how much we could expand. So that's the reason I was saying we could sometime would have a probability of saying we could play 80% of the time play tennis, but probably 20% of time we may not play tennis, right? So that's the first issue that you have to understand. Most important issue is which attribute or feature to split on. Now we do not know which attribute or feature to split on. I have considered A1 as randomly here. I could consider A2 and come up with another dysentery. A4 and I could come up with another dysentery. But then which one is the best? And which one would give me the accurate results or the prediction values? So that's one which we would be seeing in one of those algorithms called as ID3. This example. So given this training examples, understand that we have an action that is to be predicted for the users. And what we have been given is that we have author, we have thread, whether it is a new thread or old thread, the length of that particular thread that someone is trying to read, whether a user is reading from home or whether a user is reading from workplace. What is the length of the thread that we have? And whether the thread is new thread or it is the old thread that is coming. So someone is randomly reading something, and then the thread or that stuff that is there is of a well-known author or whether it is unknown author. You do not know that author before. So given this particular training example, I'd like to know, or we would like to find out if a new user reads or skips the thread, right? So let's see. Now let's say example 1. On length, we would and say length is long or length is short. So I have only discrete two values, whether it is long or whether it is short. So if my length is long, then if you see, there are 7 skips, and these 7 skips I have come up. You understand, there are 7 skips with respect to long, and reads equal to 0, right? So it's basically a negative. You see, if you would like to read and take read as positive and skip as negative, yes, reading no. So reading no is equivalent to skip, the negative one. So all these examples in this case are negative. So all of them are going to skip this particular thread. Then I simply say leaf node, you stop here. But well, if I take length and with short as the length, then we get in the output set with the value length equal to short. Please understand, we are testing at length. And what we are testing, whether length is long or short. If it is short, we could get skips equal to 2 and reads equal to 9. So in this case, we have a mixed kind of output. It is not showing whether all of them are going to skip or all of them are going to read. So skip and reads, if you could see, are 9 and 9. So total 18, right? So in this case, we need to probably expand this skip equal to 2 and reads equal to 9 as the subset that we probably need to expand further. Let's take other side. I have a thread. Whether my thread is new or whether my thread is old, in both of these cases, it is giving the mixed kind of output. Skips equal to 3 and reads equal to 7. So not all of them are positive and not all of them negative. So please understand, in this case, you probably have to expand further. On the left-hand side, I think by mistake, this has come as the leaf node. Kindly note that this is going to be a decision node. It is not a leaf node. Thread. Clear this? So example shows it is better to split on length as we reach to the leaf node faster. There is one criteria: the length of the tree should be less. The depth of the tree that find out it should be less. So I should choose length. But I do not know on what basis I would say that I should choose length. If I choose randomly, I might have any attribute that could come. So if in this training instance, the number of attributes are less, therefore we could be able to choose randomly and try to find out the process. But how the process would become longer? How many attributes you would choose at a time and every time construct a different descent tree? And that's also not giving the right answer. So the question here is how to attribute. That's the question, right? So we will, as I again said, in the one of the algorithms called as ID3, we would be seeing this, right? So another example before we could proceed. So on length, long skips, on short thread. Again, I'm splitting on thread. See why I'm splitting on thread again. You could see on the left on this previous slide, length with short, it was giving me skips equal to 2 and reads equal to 9. So therefore, I said let me expand further. Using all positive examples, great. We stop. On the right hand side, old, need to consider further. Let's consider author as an attribute. Again, go for unknown and known. With known, you all of them probably skips. And on other side, we have reads. Okay, I have not given the exam name of the algorithm as yet. I'm just giving an example. This could happen, right? We will come up with the algorithm. Shortly, I'll be telling the algorithm. So although the name is ID3. Is this clear? Any doubts so far? Yeah. Yes, it's a binary. Okay, so let's go further then. So this is a general example. Again, the same example that I had earlier. So let us keep this example. What is shown here is uh, given this all, whether we would be able to play tennis or not, right? So this is taken from Queensland in 1986, the reference, right? So now the question is, I was talking about which attribute to be chosen, whether to expand or whether not to expand, how much to be expanded and so on. So those we will now more details. So we have a solution space that is given. Now you know bias, right? So what could be the preference on this dysentery then? Or what is the bias to be applied? How do I remove the errors or how do I consider the errors? So the bias or preference dysentery would be to consider a tree which should be a smaller, which could reach to the leaf as the earliest, which can give me a decision of whether I should be for whatever attribute, target attribute considering, right? So need to search through the stop and return the value of the target feature. Decide a test on the input feature or attribute to split on. And for each value of the test, construct a subtree for those training examples with this value for the test, right? Introducing this algorithm called as iterative decomizer. Decomizer, which is ID3 algorithm. And here, this is an algorithm which is a top-down induction of dysentery, and it's basically a greedy algorithm. All right, so this is again taken from machine learning book by Tom Mitchell, and this particular algorithm is given by J. Ross Quinlan's as dysentery learning algorithm. Okay, so the input, it's like ID3, the examples, the training set available with me, the target attribute, what I am interested in to predict, and the set of attributes that I would be using for the purpose of predicting the target attribute. So the examples are training examples. Target attribute is the attribute whose value is to be predicted by the tree. Attributes is a list of the other attribute that may be tested by the learned. Returns a dysentery that correctly classifies the given examples, right? So what we are interested in is to return a dysentery that correctly classifies the given example. So let's see what an algorithm. So I have taken this algorithm from itself. Now create a root node for the tree. If all examples are positive, then return the single node tree with root with label equal to plus. So for example, my training instance is such that all of them so far saying play tennis equal to, then you simply return the single node tree root with label equal to plus. And if all examples are negative, then return the single node tree with tree root with label equal to minus. So all of them, if they're saying play tennis equal to no, then I would simply say minus. Okay, so if attributes, yeah, it's correct. So I'm coming to that. I'm coming to that. Yeah, how to decide what that which node is the starting node? I'm coming to that uh, based on some information gain concept, which I'll be explaining shortly. Is that clear? Is this clear, Professor Jaypal Leleru? Okay, fine, thanks. Okay, now if attributes is empty, so that's what I was talking about earlier. If attributes is empty, it means not all of the attributes would be, of course, empty, but if some of the attributes is empty, the single node tree root with label equal to the common value of target attributes in examples. So I this is given as a generic stuff, but well, we would have attributes. Not all of the attributes would be empty, but well, if in empty, then return the single node tree root with label equal to most common value of target attribute. So it could be play tennis yes for some of the. So otherwise begin A is the attribute from attributes that classifies the examples. Now that's the question that was the sir was asking. The question is we have to choose this based attribute, and based attributes will be chosen based on the information gain concept or entropy concept. So we will be coming to that. So A is the attribute from attributes that best classifies the examples, and let's take that particular attribute as root. So let me that the descent attribute for that root is, let's say, A. Now, so for each possible value, now values, yes, no. Now I say just yes, no, but it may be more than that. Although we are considering as for the simplicity, it's discrete valued. So for each possible value vi of A, what we do, add a new tree branch below root corresponding to the test A equal to vi. So you add a new tree branch below root corresponding to the test A equal to vi, right? So this branch that will be added will be based on A of vi or A of vi equal to no. So these branches will be formed. Let examples vi be the subset of examples that have value vi for A. So examples vi means I was talking about this. Sorry, this set I was talking about. So we have this value skips equal to 7 and reads equal to 0. That you can consider because the total skips and reads are 18, right? So only values that are available in my left hand side set would now be 7. On right hand side it would be 11. So let example be the subset of example that have value vi for A. If examples of vi is empty, then branch add a leaf node with label equal to most common value of target attributes in example. So we are again saying examples of vi is empty means there are, I mean, no examples which would have value of, or that set is 0. So read 0. So then below this branch add a leaf node with label equal to most common value of target attributes in examples. So examples we have is empty only comes when we have all positive examples and all negative, or let's say 0 examples, right? Else, now below this new branch, add the subtree. Now what the how the sub ID3 inside bracket. Now I'm what I'm doing using this step is expanding comma target attribute. Target attribute is going to remain same. Examples VM in my set is changing. Please remember that we have started with examples. Now I am saying let me start with examples of VI. Target attribute, it remains same. But now the attributes that I'll be considering will be the one which is other than the A attribute that I have already considered for expansion. So attributes minus A. So attributes minus A means now the earlier were 8 of which we have considered 1, then this becomes 8 minus 1. So all now see this is 8 A. So all those attributes that we have so far considered, right? So is this clear? In this case, we are interested in constructing a sub and we would like to expand the tree further based on the values based on the test that we would be doing for attribute A, and this will continue. Clear? So A equal to VI. So let's take one example. So A equal to A1, A2 up to AP, where A1, A2 up to AP are all set of attributes. And in this case, A1, this is the selected from all training examples. So as I said, X is the total, the entire training instance that I have. All these training examples, the selected attribute is A1. So I want to expand with A1 equal to Y. So values of A1, right? So these are the values of A1. So A1 equal to Y, that will come in X1 subset. And with A1 equal to N, that will come in this particular subset X2. Right? So that's what it is. With the attribute from attribute, select the best. For each possible value of V of I, add a new tree branch below root corresponding to test A equal to VI. And let examples be the subset of examples that have value VI for it. And if examples of VI is not empty, then we would be again adding this branch further. Okay, so then now we will be coming to, so we again run ID3 on subtree created on left with training examples that correspond to A1 equal to Y with attributes other than A1, right? So you need to decide if you would like to expand further or stop. So of course you can stop when you have all the positive examples or all the negative examples, or I'm saying, so it's one of them should be true. And if you want to split, then on which attribute to split. So again, we will be having the same question, which I'll examples. So when to stop? So all attributes are exhausted. Let's say I have a training instance with this many number of attributes, then all these attributes, when they get exhausted, A1, A2, A3 were the only attributes with A1 equal to false, A2 equal to true, again A3 equal to 3 and so on. So in this case, then we do not have any attributes to go ahead. So exhaust and say this is with XYZ percentage that we could classify the or particular attribute or target attribute. And then second, that could be all examples in the subset have same output values, either positive or negative for the target attribute. So this is clear because we have seen for play tennis, if all of the values for a particular humidity are all yes, then we should stop. Or in the read thread examples also, all skips we had stopped using a leaf node. So stop and label it as positive or negative. Okay, so now coming to that question that we had, which root node to be chosen? So you need to be smaller trees in terms of descent trees, number of nodes, or in terms of depth of a tree that we would like to see, they should be less. The heuristic to be applied is if you choose the best attribute, then the descent tree is expected to be small. But the question is, how do I choose the best attribute? So suppose X1 has 70 positive examples and 30 negative examples. Then I say we stop at X1 and we classify it successfully with 30% of errors. That's what we say. And so we stop as the split gives me the minimum error so far. So this is the split that we, after expansion of the entire tree. All right, so now let's take this example to talk about the ID3 example. I'll take at the last because there I need an information again. That concept let us see first, and then we would go with the final example. So now we have A1, we have 64 training examples, true 26, A1 equal to true 26, and it says there are 21 positive and 5 negative in the subset on the left hand side. With A1 equal to false, we have 38, 8 as positive, and so in A2 that I got, again we have 51 as true, A1 equal to true, 51, positive 18, negative 33. positive 11 with A2 equal to false. So now based on the above information, which attribute is better candidate to split, whether A1 or whether it is A2? So we have multiple methods to answer this. So let's start with the first of this, called as information gain. Now what this information gain is, which information we have gained so far from the training set. So to select the attribute that is most useful for classifying examples, a quantitative measure for an attribute measures how well a given attribute the training examples according to their target classification. So having considered that attribute, if we could give, or if that particular attribute, it separates the training examples according to their target classification, then we say that this attribute is the one which should be chosen as the best attribute at the start as a root. And of course, further, we would have all the roots. So we have to find out the information gain for all the attribute training set. And the one who results into the higher information gain, that will be treated, or that will be considered as the root node. Is this clear? And we will see how this is to be calculated. So it's a measure of how much reduction in uncertainty can be. I mean, if I choose that attribute, it's a measure of how much reduction in uncertainty can be. It's a value between 0 and 1. I want to have more information gain. Between 0 and 1 means it's a probability. How much more percentage it is against the other attributes having considered for the classification. Right? So that we have to calculate. So question, we have considered A as the best attribute. But that time I told you some best attribute will be chosen. But who would be that best? The best one is the one who is having the highest information, right? Or high information. So ID3 algorithm uses the information to select among the candidate attributes at each step while growing the tree, right? So how that would be calculated? So there is something called as some concept in information theory. We will not go into the details. We'll just take the formula of it. Entropy. In order to define information gain precisely, we use measure commonly used in information theory called as entropy. So what is entropy? It is basically a measure of disorder in the system. So I should small entropy, and I should have maximum information gain. A measure of certainty or uncertainty. So what is entropy? It is a measure of disorder in a system or a measure of certainty or uncertainty. So given a collection S of set of examples containing positive and negative examples of some target concept or target instance, the entropy of S relative to this Boolean classification, again, please note that I am taking this with considering the classification only as Boolean. It could go further with real valued attributes as well. So there we'll have to take the average, the summation of all those probabilities and take the average. But here, since I'm interested in finding out the Boolean classification, for simplicity, we are saying entropy of S equal to minus P plus log 2P plus minus P minus log of 2P minus. So where P plus are the positive examples and P minus is the negative examples in my set. So this formula, how come it has come? It is based on the information theory where log 2P bits are sent. Okay, let me go to the first. Here, understand S is a sample of training examples. P plus is the proportion of positive examples and P minus is the proportion of negative examples. So let me first cover this part and then let me go back. So it is the expected number of bits. This is the information theory. It is the expected number of bits needed to encode class, positive or negative, of randomly drawn members of S for sending certain message from let's say a node in a network to another node in the network. So what is the expected number of bits that are needed to encode a class, whether you could have it positive or negative. So if P plus is 1, then the receiver knows the drawn example will be positive. So no message need to be sent and entropy is 0. So if P plus is 1, then we say that the receiver knows the drawn example will be positive and no message need to be sent. And if P plus is zero point 0.5, then obviously P minus will also be 0.5. If P plus is 1, then P minus will, because that's probability, right? So if P plus is 0.5, then one bit is required to indicate whether the drawn example is positive or negative. So it's it's a general concept of probability which talks about any random stuff that is taken is going to be positive, whether it is, of course, the probability with half or probability with 1. So in information theory, an optimal length code assigns minus 2 log p bits messages having probability p. So that's the reason it is p into log of p for p positive examples and p minus into log of p minus. So they taken from, ID3 uses this concept from information theory, where the expected number of bits to encode positive or negative of a random member is minus p plus log of p plus to the base 2 minus of p minus to the base 2. Is this clear? So we have taken this, this ID3 is taken this particular entropy concept from information theory, where they are trying to find out what is the optimal length code that is assigned. So it gives minus log of p bits to messages having probability p. So assume this is available with me. So that we have calculated here is equal to minus p plus log of p plus minus p log of p minus. So we have entropy of S as homogeneous set, then all positives or all negatives. So in my set, if everything is, all the examples are positive or all the examples are negative, then you see if p plus equal to 1 and p minus equal to 0, or p plus equal to 0, p minus is obviously going to be 1, entropy of S is 0. So if that is the case, then I know we have a lot of knowledge or information and output is certain. And in the heterogeneous state, if p positive is 0.5 and p negative is 0.5, then half positive examples, then entropy of S is 1. You can calculate that with using that formula. You'll get out entropy of S equal to 1. Output is uncertain, and if output is uncertain, then we have no knowledge or information, and output is uncertain. Okay, so whatever this entropy concept that I spoke about, that again considering the Boolean attributes. Whether my examples will be positive or my examples will be negative, but that is not the case with our descent tree, because all the examples considering an attribute will not be positive, or all of them will not be negative. Sometimes it may be, but they are mixed. So then we'll have to calculate this entropy for other values as well. So how are we checking that? So this is the graph showing heterogeneous and homogeneous set. So if p positive is there on the x-axis and on y-axis here entropy, then you see the entropy is highest 1 when p positive is 0.5, and entropy is 0 when I have, or it is less when we have p positive at 0 or it is 1. So if you see p positive is 0 or p positive 1, entropy is going to be 0. Okay, so I hope it is clear. This concept is coming from the information theory, and we will be just using that concept for the purpose of finding our attributes with the values. So that is how the entropy. Okay, so let's now further go and see how we are going to calculate that best attribute node. Gain S comma, or information gain that we would like to calculate is The expected reduction in entropy. We would like to reduce the entropy. Please note that. Entropy should be less, information gate should be more. Now I have to choose the target attribute. So gain of S comma A. S is the training instance. A is the attribute which I'm using to find out its information gain. Now I do not know whether this. Then the expected reduction in entropy due to partitioning S on attribute A is given as gain of S comma A is equal to entropy of S. You calculate the entropy by considering all the training instances minus summation of V to values of A. So A will have two values probably if I consider Boolean classification, yes or no, into, it's summation of all S of V divided by, the values within SV after partitioning divided by the total number of values in the training instance into entropy of SV. So entropy of SV means it could be a value on the left hand side, and again we have to calculate the value on the right hand side, and we have to sum up all those, and after summing up all those on the left hand side and on right hand side, and of course taking the fraction, because SV divided by S is a fraction, so that is to be from the entire entropy of S. Whatever comes is our information gain on attribute A. Clear? So values of A is the set of all possible values for attribute A. SV is the subset of attribute A has value V. And first term, entropy of S is the original entropy of collection of S entropy. And second term is the expected value of entropy after S is partitioned using attribute A. Please note that is the expected value of entropy after S is partitioned using attribute A. It's called as resultant entropy. Is this clear? Now let's take one example. There we'll come to know doing with attributes. So given S as the training instance, and I have values equal to 9 positive and 5 negative values in S, the original set, and I have chosen attribute wind. Now I do not know why I chose wind. Right? So now on the left hand side, if wind is strong, I have 6 values which have come as strong. So my 6 by 14 is my partition on the left hand side, and out of I am getting, if my wind is strong, I'm getting 3 positive, means I can play tennis on 3 instances are saying I can play tennis. 3 instances are saying I cannot play tennis or I should not play tennis. Minus negative is 3. On the right hand side, what is weak? Wind is weak. And I have 8 such examples. That shows me that my S weak set will contain 8. How many positives? I have 6 such a positives. If wind is weak, then 6 training instances, 6 training examples are showing me that yes, you can play tennis, and 2 are saying it's negative. So S weak is S6 comma 2 minus, S strong is 3 plus comma 3 minus. Now let's calculate. How do you calculate gain S comma wind? So S comma wind would be calculated as entropy of S minus summation of values weak comma strong into SV divided by S is the fraction multiplied by entropy of SV. So entropy of, we have to consider for both. No? So therefore entropy of S weak and entropy of S strong needs to be calculated. So on the right hand side, I have given some calculations. You can find out log of 9 divided by 14 to the base 2. How this is? The formula is minus P plus log of P plus minus P minus log of P minus. So therefore entropy of S is equal to let's first calculate the entropy of S. The total examples are 14. Therefore the division it's 9 by 14 probability of positive, 9 by 14 minus 5 negative, so 5 divided by 14, that's the probability, log of 5 by 14. That gives me 0.94. Now entropy of S weak needs to be calculated. How do I calculate S weak? It is again 6 positive examples. It is log of P positive. In this case, it becomes 6 divided by 8. Log of 6 divided by 8 minus 2 by 8 because 2 is negative, minus 2 by 8 log of 2 by 8, and that gives me 0.811. Now 3 by 6 because 3 positive, log of 3 by 6 minus again 3 by 6 because 3 are negative, log of 3 by 6. That gives me 1. Having got these entropies, S wind would be calculated. Please note second step, entropy of S minus 15. Why 8 by 15? Because this is for S weak. So that is SV by S. It is 8 by 14 multiplied by entropy of S weak minus 6 by 14 because 6 strong out of 14. So 6 by 14 multiplied by entropy. Ultimately, gain of no, S strong will not be leaf node. We are just calculating gain of S comma wind. Let me finish this and then I'll come to the question. Gain S comma wind equal to minus this total calculation, whatever we have. See, 0.94 minus 8 by 14 into S weeks 0.811 entropy minus 6 by 14 into 1 of entropy of S strong, that gives me 0.0. This is the information gate that I have got for wind attribute only. I had to calculate it for all the attributes and then choose one of them as root attribute. So the question that has come, Sachin Deshmukh sir, S strong will not be leaf node as of now. We have to calculate the information gain for all the attributes first, and then we would be able to choose one of the nodes who is the base node. The one who is having highest information gain would be chosen as root node. Is this clear, Sachin sir? Yeah. So any doubt in this case? Now this I have calculated for one of the attributes. This needs to be calculated for all the attributes. Once this for one attribute you calculate, you could be able to calculate for all the attributes. But after having calculated this and considering root node, let's see what happens next. So if you see, I have taken one example where A1, this you can calculate, although I have not calculated here. This gain S comma A1 that has come is 0.27. How that has come? Again, based on the calculation of these entropies. And A comma 2 is 0.12, which is lower information gain. So I can choose A1 as the attribute. So more information gain, lower entropy in A1. Therefore, I would choose A1 as my base attribute. So this, after having this, it becomes the first step in my ID3 algorithm. Choosing the base attribute among the set of attributes which are available is the first step. So that is first, right? Now let's take an illustrated example of this ID3 algorithm. So given this data set where outlook is sunny, overcast and rainy, temperature is hot, mild and cold, humidity is high and normal, wind is weak, strong, and I would like to know whether, so I have flipped 14 to D14 and play tennis is whether it is yes or no. So those are positive and negative examples. So the first step that we should do is determine how many attributes we have. We have outlook, humidity, wind, and temperature. So determines the information candidate attribute, outlook, and so gain S comma outlook that is calculated comes as to be 0.24, 0.246, 0.151, 0.048. We had already calculated that, and then temperature comes to be 0. So select outlook as an attribute for the root node. So now we have chosen outlook as the first one. So if you see, outlook is chosen as first one. The first among the set of attributes. I have outlook as sunny, outlook as overcast, and outlook as rain. These are the values of the attribute. That now I need to consider further. Now I consider set S sunny, which contains D1, D2, D8, D9, D11 as the set. We have reduced that set, right? Because using sunny, I have got only this 5, and among the training set. I'm D1, D2, D8, D9, D11. We have 2 positives and 3 negatives. So you can see sunny. If it is sunny, you can see plate 10 is as 2, no, just 1, 2 negatives, 3, and we have 2 positive values. Clear this? You can note D11 is positive, and I guess D9 is positive. So D9 and D11 are positive. So 9 plus and 5 minus we started with. Outlook with sunny, I got 5 in my subset S sunny, 2 positive, 3 negative. Now the question, could you see the diagram? I have a question mark here. Which attribute should be tested here now? I do not know what attribute to be chosen. If you see with the overcast, we have got this 5, but 4 positive and 0 negative. So all 4 positive, therefore I conclude yes. Now, Sachin sir, this becomes yes, the leaf node. Whereas again on Outlook, rainy, 4, D5, D6, D10, D14, again 3 plus and 2 minus. So not all positives or not all negatives, unlike overcast. Therefore, again, we have a problem here. So I need to expand it further. Right? No, in this case, using overcast, we got it in the first step itself. So shall we stop there, or shall we expand further and check using? So as I said, we have to take a decision on that. Okay, let me complete first this. S sunny is equal to D1, D up to D11. Now we have to calculate gain S comma sunny with that set comma considering the rest of the attributes. I was talking about this. Yes, either positive, one of them should be positive or another of them should not be. Clear? Okay, so where we were in the ID3 algorithm? Yes, could you see now? Let examples to examples we have the subset of examples that have value we have for, and then I go with ID3 examples we have comma target attribute comma attributes minus A. So who was A in this case? That has gone now. So A is, I'm sorry. Yeah. So Outlook has gone now. Now I need to consider humidity, temperature, and Y. So please note that SNE comma humidity becomes again 0.97 we have calculated for SNE minus 3 by 5 into Y0 that you can calculate it for humidity. How many positive examples and how many negative examples? Again, you have to calculate the entropy for second term. 3 by 5 is just a portion, and minus 2 by 5 is again a portion. You have to again calculate minus log of 2 with positive examples and negative examples. Why that would have come as 0? As because using humidity as and sunny condition in the training instance, the values are 0. So using gain as sunny comma temperature, again you consider this comes to be 0.57 and gain with 0.19. So after calculating this, the question mark that is on the left hand side indicates I should choose humidity as the next attribute. Right? So that's what it is. Clear? Is this clear? The example is clear? Okay, so process then the repeat the process of selecting new attribute and partitioning the training examples non-terminal descendant node. Use only training examples associated with that node. Attributes that have been incorporated higher in the tree are excluded. And the process continues for each new leaf node until either two conditions is met. The first is every attribute has already been included along this path through the tree. So every attribute has already been included along this path through the tree. We have to consider all the attributes until they get exhausted. Then the training process would get completed, and all the training examples, or in second case, when we would stop is all training examples associated with this leaf node have same target attribute value. So it would be either positive or it could be negative. So in this case, entropy is 0. Right. So I think this is the final example, which I think this example is very common given in Mitchell's been talking about all this algorithms. All right. So, and this last issue that we will discuss and then probably will stop is determining how deeply to grow the descent tree. The overfitting, so error in the training data, some random errors, or you may have some which are not there. So stop growing the tree earlier before it reaches the point where perfectly classifies the training data. But then we do not know when to stop. If there is some problem, some values are rather than values missing, there is some error introduced and so on. So in such a case, we probably need to stop. But then it is very difficult in dysentery to stop because I never know if I expand further, I might get the probability with higher information gain. I do not know that because if you stop, when do I mean on what? On the left hand side you stop, or you can cut the depth of the tree. So that is a problem. So that's the first issue. People would have come up with some, I would say, thresholds that based on the application that would have with, let's say, in a medical history or let's say in a loan application, I could consider that based on the model that I have generated, I could stop when I get 70% of the loan defaulters, or I could stop with 80% of loan defaulters and so on, because the earlier data themselves has some errors or something. So that could be the case. Second is post pruning tree. Unfortunately, the complexity is quite more. You go on continuing with the formation of a tree. Let's be very computationally intensive. Spend a lot of time try to find out the entire tree, although as I said entire tree forming may not be possible, but okay, let's consider that you have formed the tree, you spend a lot of time, and then you post prune it, means you cut the branches, the sub branches. But then the question is where to, which one is to be uh, cut, or we would be, yeah, so the tree pruning is you'll cut the branch, or I would say you just ignore that at the end. That is what I know about, where we would be cutting one of the branch and come up with the next level. So it's like a backward tracking kind of mechanism where the entire dysentery has been formed, and then the last subtree you ignore by, taking those nodes out. That is what I understand. And then, but then the question is how much you could cut. I mean, how much you, in a in first case where stop growing the tree earlier, you are going further. I mean, it's like a forward process, but whereas in pruning, it's like a backward process. Clear? Right. And then this attribute. So I was talking about, yeah. So in the continuous attribute, you have to convert continuous attribute into discrete values. Otherwise, it is very difficult to find out how I would have my discrete values. So if you see temperature, what is the temperature value I should consider? So you have to come up with a decision saying I will be considering the values of the temperature 30 to 35 degrees, or 35 to 40 degrees, or 40 to 45 degrees, and so on. So likewise, because otherwise I may have, if it has continuous values, how many attributes we would choose? Should I choose from temperature from 10 to 15, 15 to 20, 20 to 14, and I may have multiple values, so I do not. So this is another problem. So one should come up with saying I will be considering only these many values and then calculate the attribute values. That's the reason descent trees are not good at having the attributes which are continuous. They are generally used for discrete attributes. Fine, and then we have a with missing attribute values, which I spoke about at some stage. We're saying, let's say we have a patient blood report and we do not have all the values. So some of the hemoglobin values are not there. Some of the CBC values are not, count is not there in some of the examples, and I still want to go ahead. So this becomes a bias. I mean, some of the other attributes would have a strength, that will take care of giving the result prediction. So that prediction may not be probably perfectly accurate, but that's how it is. So use the most common value of that attribute at the end of calculating the gain. So you try to find out the information gain for some of the attributes, and then based on that, you find out whether go about expanding further. So that's for patient, for missing attribute values, right? Okay, so I think this is what I had for my presentation. Hope I have to cover a bit of basics. I would say is not was the advanced kind of lecture. I do not know the participants have had earlier experience on decision learning or decision trees. They have had studied that maybe, but it was a basics from my. We have a lot of things to go in decision tree, and there are so many other algorithms as well which could actually go further. But I could just cover one algorithm within the specified I was given. So if you have some questions, I will try to answer them.
Yes, participant. If you are having some queries, then you can ask to Milind sir. If any query is not there, then we can close the session. Milind sir, for such informative talk on decision tree.
Okay, thank you, sir. Thanks a lot. I hope
If
all the
any further
participants
query
would have
is
got
there,
some.
then Milind sir or via mail or via LinkedIn.
Correct. Yeah. Fine, thank you, sir. I hope the participant would have got some insight into as what dysentery is. Thanks a lot.
Yes, definitely.
Yeah, thank you,
Thank
sir.
you.